Hello, everyone. I'm going to go ahead and derive another expression for the moment of inertia. This time I'm finding the moment of inertia for a thin disk, so you can think like a quarter or something where, the thickness of the quarter is quite thin compared to its diameter. Of course, a quarter is not exactly a cylinder because it's got a face on it and dates and all that good stuff. But we're just talking about a flat cylinder, not unlike a washer without a hole in it, or the cap of something. But anyways, it's just a circular disc who's not very thick. The difference being if it is actually a thick one, you actually get the exact same formula, and I'll probably be doing that as an example later as well. In this case, I'm only going to use a single integral, but later I'm going to do it with a double integral as well for a different example that I'll publish here, just in case anybody wants to see how it's done with multiple integrals and how much easier it is when you can do multiple integrals. So let's go ahead and get started by sharing my iPad screen with you. So now you see the wording of the problem. It says a cylindrical disk has a negligible thickness, but its radius is r and its mass m is uniformly distributed throughout the disk. Use the calculus to calculate its moment of inertia when rotated about an axis perpendicular to the disk through its center. So let's start off by writing out solution again. What we're going to make use of here is we know the mass m, we know the length, or excuse me, we know the radius r. We know that it's uniform, which in this case we're going to treat it as two-dimensional. So I'm going to say lambda, which equals dm over d a, is equal to a constant. And in fact, that constant has to be equal to m over pi r squared because that's the surface area density. Uh, we also know that dm, which could be equal to lambda dl or sigma dA or rho dV. In this case, we're going to use sigma dA for some differential mass element. We are going to rotate it about its center, and we want the moment of inertia given by I equals the integral of r squared dm. So let me start off by drawing a coordinate system. This will become really handy when we're doing in double integrals because we'll be using a specific coordinate system that's different from the Cartesian one in some sense. And it also is going to be important so we can label things. So I'm going to go ahead and draw a coordinate axis in black. So that looks pretty good. And this is going to be my x-axis. And this is going to be my y-axis. And I'm going to imagine that the cylinder is actually lying right on the xy plane, or actually on the xz plane in this diagram. And therefore, from this perspective, it should just basically look uh, like an ellipse. So I'm going to say roughly. Oops, I should do this in a different color. Sorry about that. I'm going to say roughly it will look like this. Oop, not that either. Let me try again. Something like that. Not the best, but not too horrible either. What I would ideally like it to be is not tilted, but I guess actually I'm going to go ahead and erase that. Actually, I'm probably going to erase all this junk that I've done so far. So I want to go through 3 and 3, and I also want to go here and here. So I'm going to try to draw like this. And again, that did not do it because it wasn't set properly. Let's try it again. There's our oval that we wanted, and in fact, it has a slight thickness that we might draw. That was all terrible. That we might draw by just drawing a downward line, running it around here. And then, of course, realizing that if we could actually see through the disk, we would see the bottom edge back there like this running into there. This object has a radius r and a mass m, like this. And what we need to do is use the integral of r squared dm to integrate this. But we need a differential mass element that doesn't have the distance between the a part of the differential mass element macroscopically far there are macroscopically farther from any other part. So in other words, the individual parts of the differential mass element should only differ in their distance from the y-axis by an infinitesimal amount. To do that, what we can imagine is just taking a circular loop around the axis, and I will draw that now. Let's see if we can do it. I'm going to try to go through this line. I'm going to try to go through this line. I'm going to try to go through this line, and I'm going to try to go through this line. Hopefully all this will make it turn out to be a pretty good oval. Something like that. That looks pretty good. Now what I'm going to do is imagine that that oval actually changes by an amount dr. In other words, I'm going to say the distance to this guy from here to here is just r, but if I want to go to the other edge, it's going to be a distance dr away. So it should look roughly like this, and technically speaking, it even has a thickness down here, but we're pretty much going to ignore that little thickness. And in principle, the way we work with this particular shape in like the calculus realm is we recognize that it really is two cylinders, two circular cylinders, of course. One big one whose radius is r plus dr, because specifically, like I said, this distance from here to here is dr. So the other one has a radius of r plus dr for the outer one, and then the inner one's a radius of r. So technically, the actual air volume that I'm actually doing would be the volume of the big cylinder minus the volume of the small cylinder. R, since we're treating it as if it's two-dimensional, it'd be the volume of or excuse me, the area of the big circle whose radius is 2 pi, or excuse me, whose radius is r plus dr, minus the area of the small circle whose radius is just r. So that's going to be it. The way we work this is we're going to call this shape right here dm, and it's going to be equal to sigma times dA. And dA, I'm going to tell you, is basically you can imagine it like it was just a circle that goes around, and if I cut a line, say, right along here, then I'd lay that out flat and it would almost make a rectangle. In fact, it'd be a little tilted at each end like this, but other than that, it would pretty much be a rectangle. So if that's the case, if we picture that as a rectangle, what we'd say is the length of the rectangle is the circumference of the circle, which is 2 pi r, and then the height of the rectangle would be dr. Now, that's actually our differential area element for that, and we're completely ignoring the thickness, which might be called T or something like that. But it's not that difficult to extend this to 3 dimensions. The main thing is we're going to use 2 pi r dr. Again, it was technically dA should be exactly uh, pi r plus dr squared minus pi r squared. If you actually took the time to do that, you would get pi times r squared plus 2r dr plus dr squared minus pi times r squared. You can see this pi times r squared cancels out with this pi times r squared, and all we're left with is 2 pi r dr from this and this, whereas this term that we're leaving out in here, which is pi dr squared, is a square in the differential length dr. So it's if the dr gets infinitesimally small, dr squared gets mega infinitesimally small. So that's what's going to happen here. But you can see that verifies that the formula 2 pi r dr is acceptable. Now we're going to go ahead and do that integral. So I'll also go ahead and calculate that sigma is equal to pi. Actually, I already did that. I found that sigma is equal to m over pi r squared. So now I'm going to go ahead and compute the moment of inertia. and this is the moment of inertia about the center of mass, but I'm just going to call it I. That's going to be the integral of r squared, and then dm is 2 pi, or excuse me, dm is sigma dA, which equals the integral, I'll pull the sigma out in front, integral of r squared dA, but dA is 2 pi r dr, and we're going to integrate that from r equals 0 to big R. When I do that, I get sigma out in front and 2 pi out in front as well, but I get the integral of r cubed dr from 0 to r, and the integral of r cubed dr is 1/4 r to the fourth. So I'm going to get 2 pi sigma r to the fourth over 4. Now I can go ahead and plug in the actual formula that I have for sigma that we already worked out. And when I do that, I get uh, pi, ooh, excuse me, sorry, it's still in red here. I get, just copying the results we already have, I get pi r to the fourth over 2 times sigma, and we said sigma was m over pi r squared. So you can see automatically that this r to the fourth cancels out this whole r squared, leaving just a r squared up top. And we can also see that this pi cancels out with that pi, and all we're left with is the right answer, which is 1/2 m r squared. So the moment of inertia of this is 1/2 m r squared, which matches exactly what the table in our textbook has. And hopefully that was pretty straightforward and helpful. You could, of course, make this a little more complicated if you wanted to. Let's pretend, for instance, if you wanted to make a more complicated one, you would want to pretend that lambda, that sigma, maybe it's not uniform. Maybe sigma is not a constant. Maybe sigma depends on r. You could say you could treat basically a disk that's made of progressively heavier materials as you get further and further from the center of the circle. You could imagine maybe you made the innermost part of the circular disc out of cork, and then you made it out of balsa wood outside of that, and then it transitioned from cork to balsa wood to aluminum, and then it can transition from aluminum into, say, steel. And by doing that in sort of a smooth way, you could represent the density as some constant times r, meaning that the density goes up linearly as a function of r. Then the only difference would be, of course, now instead of integrating r cubed, you'd be integrating k times r to the fourth power. But that's just a way to make it a little more complicated, and a way that I could change it up, for instance, for my students, and have it not be exactly the problem I already worked for them. So give that a try, but that's it. That's the whole example. Hopefully that helped everyone, and I will see you later. Bye bye.